I know. This lecture was on October 1st, but I figured September 30th is close
Close
enough for the
enough.
spooky season. Uh, let's see, let me also double check. I mentioned that it is sticking, yeah,
Sometimes
it
it
says
doesn't
talking,
work.
that sometimes the audio doesn't record, so I'm just double checking that. All right, let's talk about this. There it is. It's a good point now. So everybody got the formula right. Taylor, you asked about if there's an order. Yeah, you both got it marked wrong because the order of the atoms. There's not really a definitive way to do it. You typically see carbon and then the rest of the atoms go from least electronegative to most electronegative. Some places will tell you to put the hydrogen before the carbon, but more commonly you see carbon first. So this one was what? It was C16, C14.
C16.
C16, H21, NO2, something like that. So carbon, hydrogen, and then go in order of increasing electronegativity. Nobody's really gonna mark you wrong, think you're wrong. If you do it in a different order, that's just sort of the most common way I see it. If you wanted to just go straight order of electronegativity, that's probably the most technically correct.
So carbon first and then most electronegative, or most electronegative first?
So generally, I tend to see it this way more often, especially in OChem textbooks. You wouldn't be wrong to go just straight order of increasing electronegativity, putting hydrogen first, or any metals that you have would then go before the hydrogen. That's your general best practice. In OChem though, typically we see the carbons first because we care most about the carbons. But like I said, I'm not gonna mark either of you wrong either way. I just wasn't going to put all four possible permutations into the auto grader. Because what mattered most is that you could count and not put too many hydrogens on things. As far as how many are sp3 versus sp2, so the easiest way to tell if a carbon is going to be sp2 is if it's going to be sp2, it either has a double bond or it has to have a positive charge. The only other exception to that is if you have a carbon with a negative charge, that means it has a lone pair, if that lone pair is also delocalized, but that's a pretty rare situation. So for the most part, you're gonna see sp2 carbons when they have a pi bond. So all 6 of those are sp2.
Yeah.
And that one's sp2. So 7 sp2, there's no triple bonds. So there's no sp. It's the only other way you can have sp carbons is if you had a double bond going both directions, and that's also very rare. The only time we see that is CO2.
Yeah.
We will see it once to say that it exists and then never talk about it again once we get to dienes. So the rest of the carbons are going to be sp3. So 9 sp3s, 7 sp2s, 0 sp. And then how many lone pairs are present? Both of these oxygens are going to have 2 lone pairs. The nitrogen's going to have 1 lone pair. As far as which of them are delocalized. So what I was looking for were how many lone pairs are present. There should be a total of 5 lone pairs. the ones that are delocalized are the ones where there's a resonance structure, right? And the way that lone pairs show up with resonance structures is if they're adjacent to a pi bond. So in that allylic position. I always forget where the two L's are. I don't think it's 4 L's. I think it's 2 then 1, but either way, allylic. Yeah, that's right. So which lone pairs are allylic? The one on the nitrogen, so that one's gonna be delocalized into this air carbon, right? It can't go this way. Cause you're never gonna have resonance structures going towards an sp3 carbon, cause there's no room for it, and you can't break any sigma bonds. So the only resonance structure for this nitrogen would be if the nitrogen had a double bond and the oxygen pulled the extra electrons over. Are there any other delocalized electrons? How many of those lone pairs?
Yeah, both of them, because they could like switch.
Kind of,
But at one time, I think is what.
just at one, since these two lone pairs are, they're indistinguishable from each other though. And so basically, the way that the hybridization would work is that one of the sets of lone pair, or one of the lone pairs would become hybridized with the rest of them and become lower energy, and the other lone pair would basically get stuck out. So it's basically you pick one at random. And so they don't really switch back and forth because one of the sets of orbitals is lower energy than the other orbital.
It would only be one, right? 'Cause
But only
they're
one of
adjacent to
those
the
two.
pi bond.
Exactly.
Because it can't move to the right, because that one's full.
Exactly. And you can't have more than one pair of electrons participating in resonance from the same atom. Are either of these delocalized? Correct. Because this oxygen already has a pair of electrons participating in the resonance. It already has the pi bond, so you can't also give it the lone pair. Good. It's tricky to wrap your head around. It's one of those things where you think about it and you think about it and you think you have it under control, and then you go away and you come back to it and you think, no, and then you talk your way into it the complete opposite way. So it just takes practice, and we'll continue to practice at it. And then Riley, I think your question was on can we do more practice assigning priority?
Yeah.
So we've got a bunch of slides on that, but let's do the one from the quiz first. Because you both only came up with 2 more resonance structures here.
Yeah, because well, I started doing a third one, but then I was like, that doesn't work because then there's 2 positives. At least how I was doing it.
Okay. So the main thing is don't try to do too much at once. You both kind of did something similar where you moved all of the electrons at once.
Huh?
We did.
Which does kind of make sense. There is that resonance structure, but the way to systematically write it so that you don't miss any is to move one pair at a time.
Okay.
Because if you do that,
Oh, and then you wind up with more options.
then you get more options. Exactly, everything else stays where it is, but we added the pi bond over here. No, sorry. Where's my eraser? Pi bond is there, positive charge is there. And then we can do that again. And we can do that, move the electrons towards a positive charge, because a positive charge on a carbon means it doesn't have a complete valence. It's missing a pair of electrons. So then we get something that looks like positive charge here. Then we can do that one more time. I think this is the one that at least one of you drew this one. And then I think you both got the last one. You both jumped straight to the last one. Did this one, the green one, and then remember that this oxygen has lone pairs. Those
That's
can
the
move
one
over. Yeah,
So we should start like before even looking at lone pairs, just start moving the ones that are already there.
I mean, yeah, don't look at the, I don't wanna say don't look at the entire molecule, cause you do have to look at the entire molecule, but look close first. Because there's nothing inherently wrong about moving all of the electrons at once. You just tend to miss things because if you don't approach it systematically, did either of you take stats?
Yeah. I took
Mm.
it over summer.
Remember that one of the very first things you learn in stats is probability, right? How many possible combinations are there? If you don't have a systematic way of analyzing all the possible combinations, you're just kind of guessing and you're gonna miss something. Resonance structures are the same way. If you start with it as systematic as possible, then you're less likely to miss it. Same with finding constitutional isomers, because they both really are like combinatorial problems, right? How many possible ways can I follow the rules and rearrange this? So there were a total of 5 resonance structures. And I'll also reiterate, this first one is a resonance structure too.
Yeah.
So there's 4 plus the one that you started with. It's kind of like isotopes that way. People tend to take that term and say, well, anything besides the normal. But no, the normal is also one of the options, is one of the resonance structures. So there's a total of 5. If we're trying to rank them in terms of stability, most of them are pretty close to the same stability. Because what's the most important thing in terms of stability? Full octets. Only one of them has a full octet, where everything has a full octet. They're all the same except for the purple one. The purple one puts a positive charge on the oxygen. The oxygen had 2 lone pairs, right?
Yeah.
It still has 1 lone pair, so it still has a full valence. So even though we think, oh, oxygen's electronegative, I shouldn't put a positive charge there. A positive charge on the oxygen is the only way for this molecule where everything has a full valence. So this is actually our most stable resonance structure, our most significant resonance structure. And then the other 4 all have the same issue. They all have an incomplete valence on a carbon.
So then would they all be the same?
Close. I'm going to teach you how to split hairs now.
Okay.
Because it will become important later on. For carbocations, the way we would usually phrase it in OChem is the more substituted the carbon, the more stable it is. Basically, the more carbons you have around a carbocation, the more those other carbons can kind of give a little bit of electron density to it. And so it's not like it's fully empty orbital. We'll talk more about what the electrons and the orbitals look like when we do that. But for now, we can just say that for carbocations, carbocations, a tertiary carbocation is more stable than secondary, is more stable than primary, is more stable than methyl. What that means, a methyl carbocation means it has no other carbons around it. So a methyl carbocation is just CH3 with a positive charge. If you replace one of those hydrogens with a carbon, that's what we call primary. And the abbreviation is 1 with a degree sign. A primary carbocation, or a primary carbon in general, is a carbon that's attached to one other carbon. So those are both primary. Let me clean this up real quick. So since I'm explaining different, are you good if I erase the resonance structures? Actually, hang on. Let's not do that. We'll just do this. So tertiary is more stable than secondary, is more stable than primary, is more stable than methyl. Methyl looks like this. Here's our original molecule. These two are primary. Are there any other primary carbons on this molecule?
Do they have to be single bonds or could they be pi bonds?
We'll learn the difference between classifying those in a little bit. For now, let's just talk about how many carbons are connected.
Okay.
So secondary is anything that's attached to two other carbons. So anything that's in the middle of a chain, basically. I guess we're kind of splitting hairs. Does that count as secondary or not if they're attached to an oxygen? Since we're mostly talking about carbons right now, I'll erase those. Those blue ones are secondary. Tertiary carbons, if you can see the pattern here, tertiary means it's attached to three other carbons. So putting a positive charge on a tertiary carbon is preferable to putting a charge on a secondary carbon, which is better than putting a charge on a primary carbon. If more carbons around it, the more stable it is. Now, I wasn't gonna. It was a moot point in terms of grading on the quiz because neither of you got to all those resonance structures anyway.
Something about keeping it to like stable resonance structures or something. I don't know, I think I might have been just following the rules from like the notes where it was like, keep them all full, yada, yada.
That's fair, and I don't think I graded too harshly. I think it was half a point off because this does take practice and we didn't get much practice. So if I'm going back to our resonance structures here, we're trying to rank the rest of them. We already said the purple one is the best.
Yes.
That's our most significant resonance structure. Out of the rest of them, the next best thing is going to be this one, the one you started with, because it's a tertiary carbocation. where the positive charge is,
Oh.
has 3 other carbons around it. The rest of these. If we're red and blue are gonna be very, very similar to the same stability.
Yeah.
They both have a carbocation with an incomplete valence. It's secondary carbocation in both cases. I would usually classify green as being about the same stability here, but if we're really splitting hairs, putting a positive charge that close to a pair of lone pairs is gonna be a little bit less stable, because it's gonna immediately try to shift over to this. If it is all simultaneous, but in general, this is gonna be a smaller contributor than the rest of them, just because it's so close to this. So what I would have been really. All I was looking for on this quiz, since we didn't get into carbocation stability beforehand, was just that the purple one was better than the rest. Now that we're adding more details, I would say purple's better than the rest, then the original structure. Then red, blue, and green being approximately equal would have been a full credit answer too. The more and more we dissect things in OChem, the more and more we can get into splitting hairs. There's kind of always room in OChem to keep going and keep splitting hairs, just like with any science. It's 500 years of Western science that comes down to somebody's always saying, well, actually. So the main thing is that we understand this one is better than the rest of them, and this is best.
So when we're looking at most filled octets, we're really looking at the carbons.
Carbon is gonna be about the only thing that doesn't have that will ever not have a filled octet. There's a lot of double negatives in there, but I think you know what I'm saying.
Yeah.
Right, so for the most part, you're not gonna see an oxygen with an incomplete octet. And you're not gonna see nitrogen with an incomplete octet. The exceptions to that are gonna be when we get into free radical reactions. In that case, you can have cases like if you have hydrogen peroxide. And you shine light on it, an oxygen-oxygen single bond is called a peroxide bond, and they're super unstable. Because you can promote an electron from the bonding orbital to anti-bonding orbital. In the near UV or even in the visible range sometimes. And so what will happen if you do that is you wind up moving. One electron goes each direction and you wind up making. It's call it a peroxide radical. A radical in chemistry just means you have an unpaired electron. And it's super unstable. So that's a very specific case. We don't label it with a charge because technically that oxygen doesn't have a charge. If you count all the electrons, but it also doesn't have a complete octet. So we indicate that with just this like dot product symbol. We just overemphasize that there's a single electron. If we're drawing the lone pairs, we draw them like that. That's such a unique case. We'll have a whole chapter on free radical reactions. And that's about the only time you'll ever see an oxygen without a complete octet. But we're getting ahead of ourselves. So if the resonance structures are drawn for you, let's try and rank them from most significant to least. If two of them are about the same, you can say they're approximately the same.
People claiming that most significant, like the most significant is like no charge. Like, yeah, no net charge, but then like having no charge is better than zero net charge.
So that was the second variable to think of. The most important is fill all the valences that you can. And then if they all have the same number of complete valences, then you can start looking at what keeps my formal charges closest to zero. That's just totally release. And it's top heavy. That's why it has the latch. All right, Riley, what do you think?
I think C is the most, A is the middle, B is the least.
Why?
So C, there's no charge anywhere. And then A, there is charges, but they're not on carbons. And then B, there's a charge on carbon.
Not just a charge, positive charge, which means an incomplete valence, right? So in all of these, that middle carbon is sp2. It's either sp2 because it's got a pi bond in A and C, or it's sp2 because it's a carbocation. But in all three cases, and this is what we see with resonance structures. Your resonance structures, the hybridization doesn't really change, because they have to kind of keep that same geometry in order to be kind of mixing all these orbitals together. Which means this nitrogen looks sp3 here, and it looks sp3 there. But in order to make this structure A, it has to have a pi bond instead of a lone pair, which would make it sp2. So the nitrogen's gonna look planar in all three cases. We look at the optimized stable geometries here, the nitrogen will be trigonal planar, even though two of the three resonance structures, it looks like it should be sp3. Anytime you have delocalized electrons, which just means one of the stable resonance structures involves that lone pair making a pi bond, it's going to behave like it's sp2. If we were just drawing the structure for this molecule, if I was just going to draw the structure for the sake of naming it or just practicing, I would draw, you would draw the most stable. The most stable resonance structure. But we have to remember that these other ones, A and B, are still there. That's the trick, is we don't always wanna have to draw all three of these. And so it's kind of like sig figs in that you don't have to write the uncertainty when you know the rules, right? If you know the rules for sig figs, you know that your last digit is plus or minus one. It's implied. In OChem, if you see lone pairs, like Lilic to a pi bond, you know that there's a resonance structure there too, even though we're going to primarily draw just the most stable resonance structure or the most significant resonance structure. Let's do it again. Let's start with the molecule on the left first.
For that nitrogen to be negative, does it need two lone pairs?
Bingo.
So perfect.
That's one of the reasons why I do like taking notes in pen. It's because then you can't erase it and there's less temptation to try and make it perfect. But you still have to make it legible, and that's the trick.
True. Yeah, but I don't know if I don't know if they're, two of them are like the same but repeated, but they are different.
So here's one of the tricks you can do. If you've got one lone pair and 3 pi bonds. And when the pi bonds are alternating like this, we call that conjugated. So we've got a lone pair and 3 pi bonds all conjugated. There's probably gonna be a total of 4 places to put that charge.
Okay.
Which means a total of 4 resonance structures generally.
Well, would we ever give carbon a lone pair?
We are right now. Because if we move a lone pair down from the nitrogen towards the carbon it's attached to, we have to make room for that, right? Right,
That's what I was struggling with.
basically you push the pi bond out of the way, push the pi bond away. In order to make room for a different pi bond. Once we get them all drawn, then we can worry about which of these is more stable. Basically, if you're moving electrons around in resonance structures and you have a charge, it generally is gonna look like your charge is skipping a carbon or skip an atom. It's gonna jump. That's not actually what's happening, because it's actually 2 pairs of electrons moving. But the net result looks like it went from the nitrogen to 2 carbons away. And then from that carbon, you go to alternating carbon. So where's the last one gonna go? So now, which of these is most important? Most significant?
The one that we were given,
Why?
because all of the carbons are full.
The carbons are all full here too.
Well, one of them has a negative charge, so it's over full.
So the questions, but the nitrogen's over full in the one we're starting with.
The nitrogen doesn't matter, we care about the carbon.
We care about everything, but you're right,
But we have favorites.
but we have favorites. Where is it gonna be most likely? If we have to put a negative charge somewhere, where are we gonna put it?
Not on the carbon.
Why not?
Because we like it the most, so we're nicest to it.
Yeah.
What types of atoms, what property of different elements means it's better at pulling electrons towards itself?
Right? Most electronegative.
That's the one.
I was gonna say, your mom analogy is an analogy right now.
So. Out of all these, they all have, everything has a full valence in all these. And with negative charges, you're not gonna have an incomplete octet because you have extra electrons. It's 2 complete, but it's still, each of them still only has 8 electrons though. If we look at a carbanion, if I drew out the complete structure for this red one here.
True, but somehow still have 4 drawn.
This is the one we started with.
Yeah,
double bonds,
oh,
right?
that's what but I still have 4 drawn. I think cause I just counted moving the
See,
double
I
bonds
did-
on the
I
inside
did this one too.
as one of I counted this one as one of the structures.
Yeah, the one that you have as the one that we started with, we had as a different resident structure than the original.
Not technically wrong.
Okay.
Okay.
Generally speaking, I don't consider rotating the pi bonds inside a benzene ring to be a different resonance structure.
Okay.
But yeah, you technically could have a fifth resonance structure that looks, where the only thing that's different is you shifted those double bonds around. That's fair.
I was like, wait, I have 4 drawn, but I'm missing
And you're
one.
still missing one. Yeah, that's what it is. Good call. So if we look at this carbon that has the negative charge on the red structure. It's got a lone pair plus the hydrogen that we didn't bother drawing because we were doing skeletal structure. Plus 2 other sigma bonds, so it's still 8 electrons. Just one of them being a lone pair instead of a bond means that in terms of formal charge, it owns both of those electrons outright instead of sharing them. So they all have the same number of complete octets. They all have all the way full octets. So then if we're splitting hairs, then out of these, our next most important variable is that if we're gonna have a negative charge, it's gonna go on the more electronegative element. Because electronegativity means it's better at pulling charge towards itself, right? We extend that logic just a little bit. Something that is more electronegative is going to be more stable with a negative charge. Because it's better at pulling the electrons in, right? In this case, to go back to the blanket hog analogy, it's like giving something that's electronegative a negative charge is like giving the blanket hog the entire blanket. That doesn't mean that you can't give the non-blanket hogs the entire blanket. It's just if you're gonna give the entire blanket to one of them, who's more likely to give up and just let the other person have it is gonna be the one that's less electronegative. This one's shorter. Has one fewer resonance structure at least.
But don't just rotate the double bond inside the ring.
Well, so this one, and this is an important thing that I always forget to emphasize because it's one of those things that's kind of second nature when you get used to it. This isn't a benzene ring.
Oh, because the nitrogen's in it.
And because these 2 carbons are sp3, they don't have double bonds. It's a hexagon, but hexagon does not mean benzene. Benzenes and aromatic in general.
Yeah.
Even if there was a nitrogen as part of this, that would still work. But you need to have all of the carbons or all the atoms have to be sp2 in order for it to have that benzene-like structure. These carbons are sp3, which means no resonance.
What if none of them have double bonds? What if it's just a single one?
So then there's no resonance that can happen. So like even if one of them was a nitrogen,
Is it still a benzene ring?
no,
What is it?
that's cyclohexane.
Okay.
So the difference specifically, and if we draw out all the complete structure, it's you can see that each one of those carbons has 2 hydrogens. So all of these carbons are tetrahedral, they're all sp3. And so no resonance happens in this case. Even if I erased 2 of these. and made it a double bond. Now it's cyclohexene instead of cyclohexane, but still, there's no other pi bonds or no other lone pairs around that can cause any resonance because there's nowhere for these pi electrons to move. It can't do that because it'd be moving towards a carbon that already has a full valence, and they're all sigma bonds, so there's nowhere we can push the other electrons either. Alright, so
But you would never have cyclohexane, the 3, because that would just be benzene, right?
you would never have, it's cyclohexatriene
Oh.
is the way we would name benzene normally.
Okay.
Cyclohexane would look like this. A triple bond in a ring structure. That can happen, but that also has no resonance.
Can't put them anywhere.
Right, so as soon as you do this though. That has one resonance structure, well, two technically. And as soon as we do that, now it's benzene. You have to be able to resonate all the way around for it to be. We will get into the definition of aromatic in more detail in a few chapters. But basically just know that you can't have any sp3 carbons in the way. Or because you can't have a resonance structure that goes through an sp3 carbon. You did that wrong.
So,
You haven't even done your own.
no, because if I just copy it once, then it makes all the other ones faster, because then I could just duplicate it like 500 times.
Interesting. I didn't know that. Okay.
You might just do this. And then put it- I just might get rid of these ones because I don't care about seeing one right now. Okay. And then I have this one that I can just duplicate 500 times.
And then you just switch the stuff around.
Different doors.
Oh.
Yeah. Are you already drawing ones or do you, that's
This is the one we started with, right?
The bond is on.
Oh,
The bond and the positive.
then yes, I already drew one.
How you learn till you gotta get things wrong to them.
Sorry, show it to me.
I know, that's why I had her show it to me too.
Alright. So positive charge on a carbon means it has an incomplete valence, which means we can just move electrons towards it. And the way it's drawn here, there's really kind of two options. We have two things that can move electrons towards it, right? One from each direction. Because you've got,
some single friends on N.
Good job, Jay.
a lone pair.
Some single friends.
Single friends.
They're ready to
Friends are
mingle.
a lone pair, I like that.
They're single.
So single friends can swoop in and fill the gap.
Yes. Would that become a pi bond to fill the gap?
It would, exactly.
Like, okay, so I've been noticing every time I draw my arrows, I've been noticing either like if it's coming from a carbon or an N. No, because it doesn't go to the carbon, it goes to the line.
It doesn't quite, because it actually is going to move. We always draw these arrows, and this is going to become one of the most important things about mechanisms, is you always draw the electrons moving towards a nucleus, because the nucleus is where the charge is.
Then I guess I've noticed the pattern that if it comes from an element, it goes to a bond, and if it comes from a bond, it goes to an element when you're drawing your next one. That makes sense what I said.
Yes, I'm just, you know how I dislike absolutes.
I've just noticed a pattern. Is what I
Yes.
said.
Yeah, so if it's a lone pair and you move a lone pair towards a charge, towards a positive charge, then you're gonna make a pi bond. If it starts as a pi bond and moves away from the other atom, it turns into a lone pair. Yeah.
The one for the homework, we just moved the double bonds around for a couple of them, right?
But that's just like the benzene ring being all magical
We-
pony.
But then it comes down here into these.
When we did that,
Yeah,
we started by moving a lone pair. So in this case, we were moving a pi bond towards a charge. So
okay,
so it's, yes, that's the exception, is if you're moving a pi bond towards a positive charge, you can make it go from pi bond one direction to pi bond the other direction. And that's what we're gonna see in the next one right here. And because the other thing we have that can donate electrons to fill that incomplete valence.
it's on the nitrogen.
So for the second one, if we ignore the nitrogen lone pair, we can move the pi bond over just like we did on the homework one, in which case nitrogen stays the same way it was. Get a pi bond there and a positive charge there. So again, for the blue structure here, it looks like the charge jumped to carbon, right? That we alternated. But really what's happening is we took the pi bond away from one carbon and moved it towards the other carbon. But as soon as we did that, we made something that's not stable, so it would want to go back the other way, right? So that's kind of what goes to that. It's both of these at the same time. So out of these, which one's the most stable?
Do we really only have 3?
Yeah.
We can't just like move the guy around on the inside of the ring and then have positive
No, because
all
they're
over the
full.
place?
Because these other
Then you can't move
carbons,
it to full friends.
exactly,
They're not.
They're married.
They're not
Can't mess
single.
with them.
They're married.
yeah, sigma bond is closer to being married than it is. Pi bond is a little bit more fluid.
Pi bond is dating.
Pi bond is dating in an open relationship.
I like my analogies, you guys. You gotta do what works.
Yeah. Right, so, and that's what we were talking about how, what makes it benzene is if we had double bonds all the way around, then yeah, there'd be more. And that's why the number of lone pairs and double bonds is what's gonna be closely linked to how many resonance structures we have. We had a lone pair and we had a pi bond and we had an incomplete valence. There's only so many ways we can arrange those. As soon as we add another pi bond in there, then there'd be one more place we could move that charge.
We don't have a lot to play with.
Exactly. And so, if we were looking at this molecule from the beginning, we're looking at where is the pi system? Do you remember me using that phrase last week?
Slightly, remember.
So the pi system is basically the average of all the resonance structures. So the pi, or the superposition technically, but basically if you overlay all the resonance structures on top of each other, where do you see pi bonds? So for this structure, the pi system would go basically that whole part of the molecule. Because there's a pi bond here, you can put a pi bond here, you can put a pi bond here. So the nitrogen lone pair is being delocalized, this pi bond being delocalized and having that sp2 carbon in between, that whole part of the molecule has pi electrons. Because it's gonna look like the average of the red, blue, and black. Sometimes the way that you might see that drawn, if they're trying to draw one structure to show the pi system, is they basically use a dotted line for the second bond. Whereas there's the pi system, so you might see it drawn as. And then where you put your chart, and then what you would do is you would just put brackets around the whole thing and say the whole thing has a positive charge.
Okay.
I don't like that because like you said, I don't think it's I would rather draw it like this. Draw the most significant resonance structure, and I just want you to know there are other resonance structures as well. The other place you see this is on benzene, and instead of drawing the circle, sometimes they'll just draw a dotted line all the way around the inside of the hexagon. That's the way I like it better. But so I would prefer to see it like that. Some textbooks will draw it like that. Great.
It's fine when you're typing, but not when you're taking notes.
I think MoldView even will do a 1.5 bond. It'll actually draw that if you, in one of the sub menus, you can have it draw 1.5 bonds, but like I said, I don't prefer that. I would either draw it like this or just draw all 3 pi bonds. And drawing all 3 pi bonds, frankly, is better for getting practice drawing your resonance structures, because then you can actually draw your arrows more reasonably.
But the other 2 structures that we have would be about the same.
The
Yes.
original and the blue.
Because in both of them, they're both a secondary carbocation. The most stable is going to be the one where the nitrogen has the positive charge, because nothing has an incomplete valence. All right. Last one. This one's quick, and then we'll take a break, and then we'll talk about acids and bases when we come back. Are these the same structure? Are they resonance structures, or are they isomers? Can you start from one of these and draw arrows to get to the other one?
Yes.
So does that make them resonance structures or isomers? Resonance structure. So at the very least, we can look at and say, okay, well, all those carbons are sp2 in both of these, right? So if all of our carbons are sp2 and they're all in the same spot, that's an indicator that it might be a resonance structure. That would be one resonance structure, but if we're trying to get all the way to that one, then we could.
Yeah.
Which is gonna look like. That's our other molecule, right?
No, that's the same.
Yeah, that is not the same, because then I have my negative and then it just migrated.
So you can't do that top arrow because that
That's with the
oxygen
negative.
already is a negative, not a positive. Good. So which of these is gonna be more stable then?
On the left,
Because,
because we like carbon better. No, the oxygen is more electronegative, so
There it
it's
is.
more stable when it's negative than a carbon.
anytime I ask a why question, it's either resonance or electronegativity, right? So. Because the oxygen is more electronegative, if we have to give something a negative charge, we're gonna give it to an oxygen. All other things being equal. The exception to that, the time when you can put a positive charge on something electronegative is when it fills more valences that way. And going back to the problem from the quiz. The most stable structure looked like this, right? And then had all the other
Yeah.
bonds continue off that way. On the face, if you just looked at electronegativity, you would say that this would be less stable because we put a positive charge on an oxygen. Oxygen's more electronegative. It shouldn't get a positive charge. But this is the only way that we were able to fill all the valences, and that matters more than electronegativity. In 99.9% of the cases. The only time that's not the case is with fluorine. Fluorine is so electronegative, it won't form a double bond no matter what.
Okay.
But we're not gonna deal with fluorine in this class because fluorine is way too reactive. You can't even there are labs that specialize in putting fluorine on organic molecules because it's so difficult to work with fluorine.
So we don't need to know that.
So you don't really need to know that. All right, let's take a break. Let's come back at 10 after. And we'll talk about acids.
Where are you going?
Yeah.
All right, let's talk a little bit about acids. We'll talk a little bit about some science history too, because Arrhenius was a very important figure. First off, his first name is Svante, which is just a cool name. And he was either Swedish or Norwegian, I don't remember which. Nordic. Svante Arrhenius, he gets remembered the most because he was one of the first people to define what an acid was. And he kind of defined it in terms of the solution. But the other two other things he did is, you remember the rate law equation? So rate law was rate equals K times concentration of your reactants. K, we had an equation for. Arrhenius came up with this equation. The A in that equation is for Arrhenius. And perhaps most importantly, this is what he won his Nobel Prize for. But most importantly, he was actually the first person to publish data showing that anthropogenic climate change was real in 1880s. He published a paper where he crunched the numbers and looked at the Industrial Revolution and how much coal they were burning, and said, we're going to significantly increase the amount of CO2 in the atmosphere as a species by doing this. He actually thought it might be a good thing because he neglected the disastrous weather events, and thought, well, warmer means less permafrost, which means more land for humans to farm. I blame that partly on him being from Sweden. But yeah, and it's interesting, it was closer to the beginning of the Industrial Revolution than today. So it took the rest of humanity and capitalism a few, 100 years or so to catch up and actually start paying attention. And actually, the stuff he published actually tracked with a few minor corrections. If you just use his original model that he published in 1880, it tracks our global ocean temperatures really, really well. It's off by a couple percentage points that they then corrected for, because he didn't have all the data in meteorology that we have now.
When he came out with that, did people believe him?
The scientists did.
Okay.
But again, nobody really thought that was gonna, if you say, oh, one degree Celsius back in 1900, nobody thought that was gonna be a big deal. Like, oh, cool, fewer cold days,
Yeah.
less snow, that's a good thing. It wasn't until the 1980s, late 1970s, that the petroleum companies started understanding how disastrous it was going to be, and they buried all that information. Anyway, back to the matter at hand, acids. This is sort of the most basic wrong term. The most foundational understanding of an acid, because it just looks at the entire solution. So if you put something in water and it increases how much H+ you have floating around, it's an acid. But that doesn't really, one, it doesn't look at what's actually happening, and two, it doesn't take into account, well, what if you're not in water? So the Bronsted-Lowry definition is what we're going to use for the most part, and that's what most people think of when they think of acids, is that proton donor definition. If you can give away an H+, if you give away an H+, that makes you an acid. The third definition, in Gen Chem, we kind of ignored that, right? We just said it's there, but we're not really going to do much with it. When we talked about equilibrium a little bit, we talked about how you can put metal ions in water and they can act as an Arrhenius acid to make the solution more acidic, because they accept electrons from the water molecules, which makes the water molecules themselves more acidic. We're going to talk more about Lewis acids when we start talking about mechanisms, because that'll actually become important. But for now, we're still going to come back to Bronsted-Lowry acid is our primary definition. There we go. Sorry, the slides are a little out of order. Bases. An Arrhenius base just means it increases the concentration of hydroxide ions, which makes sense now that we understand equilibrium, right? Water in particular always has that auto ionization factor. So if an acid's gonna increase your concentration of hydronium, a base is gonna decrease your concentration of hydronium, which in terms of what we can actually measure, increases your hydroxide concentration. All review, all pretty foundational to acid bases in Gen Chem, right? We spent a whole chapter on that, and this is probably the end of the second quarter. If a Bronsted-Lowry acid gives up an H+, a Bronsted-Lowry base accepts an H+. Basically, you were never gonna have just H pluses floating around by themselves. They're gonna find something with a lone pair to glom onto. So we will never have an acid reaction without also having a base reaction. Or more commonly, we have an acid-base reaction. We have both of them, just like a redox reaction. You can't have reduction without also having oxidation. You can't have an acid without also having a base. And then if you think about, so Lewis acids were, the way that I remember Lewis acids and Lewis bases is you flip the charge. Lewis acid and bases are talking about electrons instead of protons. So donor and acceptor get flipped as well. Right, so if a Bronsted-Lowry base is a proton acceptor, it's also, if it's a Lewis base, it's an electron donor. Right, and so these are all review slides. So for instance, if you put HCl in water, the HCl reacts with the water, the hydrochloric acid acts as the Bronsted-Lowry acid and gives away the H+, and you make chloride and hydronium. And it's still also kind of it also still works as a Lewis acid and Lewis base. You can use that definition here too, because if we actually look at what's happening, there's a lone pair on the oxygen that's basically grabbing the H+, right? So the oxygen now has less electron density than it did, which makes it the electron donor. By accepting the proton, it's also donating electrons. Right, so they're not mutually exclusive. They're all, generally speaking, at least two of these will be true at any given time. Even if you're not in water and you can't use an Arrhenius base, you could either define it as being Bronsted-Lowry base or a Lewis base. Bronsted-Lowry is just the more common way to think about it. More applicable to biochemistry because we talk a lot about protons and H pluses in biochemistry. All right, and so you remember conjugate acids and conjugate bases? Vaguely? We're going to, instead of doing it like this where we label acid base, conjugate base, in OChem, we're going to talk about conjugate acid base pairs a lot more. Instead of talking about here's the reaction, what's the acid, what's the base, we're going to be talking about the molecules. And saying, okay, does this molecule have the proton or not? Is it in its acidic form or in its basic form? So we're gonna basically talk about like, okay, HNO2 versus nitrite. they're all always paired up, right? So if you have a bunch of nitrite in water, what we're gonna talk about in OChem is basically, is it in its acidic form or is it in its basic form? Is it in its, and the way we'll talk about that is the protonated form versus the deprotonated form. Just, I guess I didn't review the fact that we use the term proton to just mean an H plus, a hydrogen ion. Right, so the conjugate acid base pair is these two, so it's gonna be more in the context of similar to the way we talk about buffers. We're gonna use the buffer equation actually a lot, but not just to make buffers,
You said proto means,
just an H plus. So proton donor means it is giving away an H plus ion. So H3O plus versus H2O, which is the protonated form and which is deprotonated.
the left is a protonated,
Yeah,
it has more.
it has the extra H plus. Which also means it's the one that can act as an acid more readily. It's easier for H3O plus to give away an H plus than it is for water to give away an H plus. Water can give away an H plus, but not as easily. Alright, so let's do some practice with some organic molecules instead of just polyatomic ions. If you put this molecule, which is called phenol, with hydroxide, you can deprotonate the phenol. What's the acid? What's the base? What's the conjugate acid and conjugate base?
The left is the donor, the proton donor,
Which makes it the
acid.
acid. Which makes the hydroxide base. What does the hydroxide turn into once it accepts the H plus?
The H2O.
The H2O. Which makes that the conjugate acid.
Good question for a minute, 'cause I was like, it's right in front of us.
Yeah, in a lot of ways, acid-base chemistry in OChem is simpler. Because you can actually see the molecules a
I
lot
don't
more.
remember a lot of it, so.
We'll get you there. So then that makes the conjugate base. The deprotonated phenol. And so again, the other way to think about this in turn, instead of just thinking about it in terms of here's a reaction, what happens is the phenol has two possible states, protonated and deprotonated. The water has two possible states, protonated and deprotonated.
So conjugate base is always gonna be the deprotonated and the conjugate acid is gonna be the protonated.
Correct. This looks a little bit weirder. Or like something a little bit new at least. What's the acid and what's the base?
Acid is the one with the nitrogen.
Why?
so it has more than once.
It has more electrons than it wants.
Isn't it about having more hydrogens?
It's acids and bases is about the hydrogens. So what's the molecule that's paired up with this one? What's the molecule paired up with it on the product side? I just meant, like, it's still the nitrogen molecule, right? What's different about the nitrogen molecule? Which means did it give up an H plus or did it accept an H? Which makes it the base.
So you don't even really need to know how many H's there are.
Not for this slide, not just to figure out what's the acid and what's the base. We'll talk about
Can we stick?
how do we know if I don't give you the products, how do you know what the products are gonna look like? And whether you favor the products or reactants at equilibrium, that's the real trick. And that's part of what we're gonna spend a decent amount of time on in OChem.
So then on the right side, it's the conjugate acid. The one with the nitrogen.
Yeah.
So the deprotonated nitrogen is the base form. This is the conjugate acid. My color coding went away there.
I'm still color coded, so it's fine.
So this molecule, you don't even need to know how to name it. This molecule gave up an H plus, which makes it an acid. All right, so let's apply this to more specifically to organic compounds. We had a functional group already. That's already named as an acid. This carboxylic acid is named as an acid because when you put it with water, it acts as an Arrhenius acid. It increases the amount of H3O plus.
Isn't that one of the ones we made slides or flashcards for?
Yeah.
Carboxylic acid?
Exactly. So when you put a carboxylic acid in water, the acid group gives up the H plus. The water accepts it. So the water is the base, is acting as a base. Which makes the hydronium the conjugate acid. And the deprotonated form of the acid is the conjugate base. Right, so when we say protonated versus deprotonated in acid versus conjugate base, it's always about this molecule can give up an H plus and what does it turn into? All right. Quick review. We're not actually going to do any of the math for equilibrium much in this class. But this should look familiar, right? When we had a weak acid
Yeah, it does.
with water, you always had the same reaction. Didn't matter what your weak acid was. That HA could be anything. In this case, it's acetic acid. But anything that can give up an H plus could react in the same way, right? So then the question was, how do we predict whether the products or reactants are favored or by how much? How do we predict what the pH is going to be? And that's where the equilibrium constant came in. If we remember our definition of pH though. And we can remember that P, that lowercase p was an operator, which just means it's a function. Just like f of x just meant whatever x is, you're gonna do the same math to it, right? P just means whatever we're talking about, you're taking the negative log of it. Which means we can apply it to more things than just hydronium. That's still gonna be the way we talk about how acidic a solution is. It's still gonna be talked about it in terms of pH generally. But it also gives us a way to talk about relative strengths of acids. Instead of just looking at Ka, sometimes it's a lot easier to think in terms of pKa. And that's gonna be the number one way we talk about how strong an acid is, because as we start to favor the reactants, as the equilibrium favors the reactants more, that makes it a stronger acid. It's better at giving away the H plus, the more hydronium we can make at equilibrium, right? Which in the equilibrium constant, what's the first rule of equilibrium? You didn't have me for equilibrium, so you can be excused a little bit. I drive this home a lot. Do you remember, Taylor? First rule of equilibrium is products over reactants.
Second rule is also products over
It is,
reactants.
exactly. So as we start to favor more and more products, as your acid gets stronger, what happens to Ka? Does it get bigger or smaller? So if a stronger acid makes more product, right? So if you're making more product, what happens to this ratio? You have less reactants left. The
Wait,
top half of this ratio gets bigger
The bottom half gets smaller.
and the bottom half gets smaller.
There's a take from it.
right.
All of that to say, the stronger the acid is, the bigger Ka is. Basically, if Ka is greater than 1, that's almost our definition of a strong acid. Because remember, in terms of equilibrium versus just going to completion, we said that a strong acid just meant we treat it like it dissociates 100%, right? If Ka is greater than 1, that's a strong acid. If Ka is greater, I guess, let me rephrase. So stronger acid means Ka gets bigger. What does that do to pKa? Because of that negative sign in front of it, right? So the stronger an acid, the smaller the pKa value. All of that to say, this is how we usually look at how strong an acid is and whether an acid can protonate something else is by looking at tables like this, where we have pKa of different functional groups or different molecules. So hydronium has a pKa of negative 1.74. Which means anything that's more negative than that is going to act as a strong acid in water. I'll say that again in a minute. Basically, the lower pKa, the stronger the acid. The higher the pKa, the stronger the base, the stronger the conjugate base is. Right, so up and to the left, those are your strongest acids. But that also means that's your weakest base. Something is a strong base if it's good at grabbing H pluses, right? Well, if the conjugate acid is good at giving away H pluses, then the conjugate base is not gonna be very good at pulling them away, right? So the better an acid is, the weaker the conjugate base will be. So your strongest bases are gonna be down here. So how do we use this information? Well, if I give you two molecules and I say an acid base reaction happens. How do you know what's gonna act as the acid and what's gonna act as the base? You go to this chart. So if I said H2O plus acetic acid. Well, water shows up in two places, as an acid and as a base. Here's acetic acid. How do we know what's gonna do what? Is water gonna act as the acid here and give the H plus away, or is water going to accept the H plus?
Gonna accept the H plus.
Because water is not a good base, but water is a better base than it is an acid. And so basically we rank them, we look at this, if you can find them both on the same chart here. Whichever one of your acids is higher at the top, that's the one that's gonna act as the acid. So that's gonna allow us to say it's gonna make H3O plus and the deprotonated form, which looks like this. And so we just stole the H plus from the acid, more accurately, the acid, and it pushed it away onto the water. So now, how do we know whether the equilibrium is gonna favor products of the reactants here? This is acetic acid with acetic acid acting as the acid, water acting as the base. How do we know whether we favor products or reactants at equilibrium though?
These products of reactants.
First rule of equilibrium is products over reactants. And now we look at two conjugate acids. So there's one of our possible acids. Here's the other possible acid. Which one of them is a stronger acid? So now we're comparing these two.
Oh, second one.
Hydronium is a better acid than acetic acid is. So even though when we put acetic acid with water, acetic acid can give away the H plus some of the time, but it's making something less stable than it started with. So the difference in these pKa values tells you which side is favored. This one's it's gonna favor the reactants. The reactants are going to be more common in equilibrium than the products are. Because H3O plus is better at giving away a proton than the acetic acid is. Think of the proton kind of like playing hot potato. If you initially start with just one person having the hot potato, they're gonna push it away to somebody else, right? But if they're pushing it to somebody that's stronger than them, 9 times out of 10, it's just gonna get pushed right back to them. So even though acetic acid is an Arrhenius acid and it drops the pH and it can act to give away an H plus, it's not very good at it when you compare it to water. Or more accurately, it's not very good at it when you compare it to hydronium. So can we do anything with these numbers here? And I'm gonna show you something with that really quick, and then you're gonna I don't mean to underestimate you too, but it's one of those things that's gonna take you more than once to see it before you really grasp it. The difference between these two has a exponential relationship because of this log term in there, right? If we want to know what the equilibrium constant is, not just that it favors the reactants, we actually want to put a number to the equilibrium constant. We look at the difference in the pKa values. The difference in these pKa values is 4.75 minus negative 1.74. That's going to be really close to 5.5, 6.5. The Ka for this reaction is going to be really close to 10 to the negative 6.5. Right, so we can actually use these Ka values to see roughly what is the ratio of these two states at equilibrium. And that allows us to say things like at equilibrium, you're going to have a roughly 10 to the 6.5 to 1 difference in concentrations between these. And we'll actually work out some of the math. Next time. How do we apply this to, if we have a big molecule like this, propranolol, it's got a bunch of different functional groups on it, right? How do we know which proton is going to be is the most acidic here? We look at this chart. This chart has individual molecules on it, but we can extrapolate and say, okay, well, any sp3 carbon is going to have something close to a pKa of 50. Any nitrogen, sp3 nitrogen, is going to have a pKa close to 38. Here's all of our alcohols. Right here, water, ethanol, and T-butyl alcohol are all between 16 and 18, all relatively close to the same pKa. So basically we can generalize about different functional groups based on charts like this. So if we're looking at this, if we're looking at all the different functional groups or all the different places where we have hydrogens, we have sp3 carbon hydrogens. Are those going to be the most acidic hydrogens? No, that's all the way down here. That's our least acidic type of hydrogen. Any other type of hydrogen is going to be easier to remove than an sp3 carbon hydrogen bond. What about these aromatic hydrogens? Well, that looks,
I mean, wouldn't they also just be SP2s though?
it'd be sp2s, so we put them down in this category, right? also not very acidic. Generally speaking, carbon hydrogens attached to a carbon are not gonna be very acidic. So we should start looking at other groups.
So like our OH.
So we've got an OH. We don't know exactly where the pKa is gonna be, but we can be pretty sure it's gonna be in this general range, somewhere between in the 16 to 18 range. The nitrogens were all the way at the bottom as well. Are there any other types of hydrogens on there?
One from the nitrogen.
One on the nitrogen is a possibility,
They're what's connected to it.
but we already looked at those a little bit, right? Those are all gonna be kind of down in this range, right? They're all sp3 carbons. So really, it's the oxygen and the nitrogen that are closest. And nitrogens generally have a pKa around in the high 30s. Alcohols have pHs in the high teens. So what's the better acid? The alcohol. All right. That's a good place to stop. We'll review this. And then we'll talk about how we can use those pKa's and pH to affect solubility. And then next week's lab, this week's lab, we're just finishing up last week's lab. So I think there's a few more melting points. We're gonna do that recrystallization. Next week's lab, we actually have a lab that's all about how do we affect solubility by changing pH. And that's what we'll talk about on Thursday. Go get some lunch,